So, let us construct some two-dimensional crystals, and we will be able to illustrate certain concepts which we could not illustrate in one dimensions, especially related to rotational symmetry. As before, we can generate a two-dimensional crystal by starting with a two-dimensional lattice and decorating it with a two-dimensional motif. We can relax this constraint of the two-dimensional motif by either putting a one-dimensional motif or a three-dimensional motif to get a two-dimensional crystal. But for now, we will only consider two-dimensional motifs which will be used to decorate a two-dimensional lattice. So, the first example is the simplest of the lot, wherein we start with a square lattice and we put a circle, a green circle as shown in the right hand side, as the motif which goes on to decorate this lattice. If you look at the lattice, we have considered this before. The lattice has certain symmetries like the fourfold axis at the lattice points and a fourfold axis in the middle of the unit cell, which is shown in the blue color. Additionally, it has got two-fold axes and certain other mirror planes, which we shall consider very soon. The important point to note is that we have not shown all the symmetry operators overlaid on the lattice, and that is for the sake of clarity. Now, how is the crystal? The crystal is the one which is shown on the right hand bottom side of the figure. So, we get a crystal, and the unit cell of the crystal is the one which is marked in blue. Therefore, now starting with the square lattice, by putting a circle motif, I get a square lattice as shown here, a square crystal as shown here. Now, the important word here is that the lattice is called a square lattice, and the crystal I have generated is also called a square crystal. That means I am using the same word in more than one context, the word square, in the context of first of all in the context of a lattice, second in the context of a crystal, and additionally I can use the same word to describe the shape of the unit cell, which is also a square. Now, let us try to understand why this is a square crystal. If you look at the symmetry of the lattice, and the whole symmetry is overlaid here, it has got a symmetry which can be written in shorthand form as 4 mm. So, what are these 4? The 4 stands for the fourfold axis, the m stands for, say for instance, the vertical mirror, the mirror 1, and the other m is for the diagonal mirror. Therefore, the symmetry of this lattice is 4 mm, which happens to be identical to the symmetry of the crystal. The symmetry of the crystal is as well 4 mm. Therefore, the symmetry of the lattice and the symmetry of the crystal are identical, and the symmetry happens to be 4 mm, and therefore, as when we make a listing of all the crystals, we will see that whenever I have a symmetry 4 mm or a symmetry 4, such a crystal is called a square crystal, and therefore, I will label my crystal which I have generated here as a square crystal. So, we can evolve a principle here that if the symmetry of the motif is greater than the symmetry of the lattice, then the symmetry of the lattice is conserved when I go and make a crystal, and that, in other words, the symmetry of the crystal will have the symmetry of the lattice, and in this case it has got a 4 mm symmetry, and the symmetry of the lattice and the crystal are identical. Now, what is the symmetry of the motif we are talking about here? Here we are talking about the symmetry particularly only of the circle motif, not of the lattice, not of the crystal, or nor of the unit cell which we have considered. We see that this motif, any fold rotational axis is allowed, which of course has to pass through the center of the circle. We also notice that a mirror in any orientation passing through the center is also allowed for a circle. Therefore, it is one of the most symmetrical objects, the circle, in 2 dimensions, and additionally you can also conceive of a center of inversion at the center of the circle. Of course, we had pointed out this before, that in 2 dimensions we do not have to invoke the concept of an inversion, but in any case we see that center of inversion also is present at the center of the circle. So, you can see, since a circle is a highly symmetrical object in 2 dimensions, it has got a symmetry which is higher than the symmetry of the lattice. When I put such a motif on top of a lattice, I do not lose any symmetry, and the symmetry of the crystal is preserved, and in this case the symmetry of the crystal happens to be 4 mm, and because it has got 4 mm symmetry, I would call it a square crystal. Now, let us do another example and another exercise, and this time I will again start with the square lattice as shown here, but this time I will not decorate it with a circle, but instead with a square. And you can see that this is not a square in any random orientation, but it is oriented very similar to the unit cell of the lattice. So what I do, I take my previous square lattice, which we saw before was generated using basis vectors A and B, where mod of A is equal to mod of B. And now I make a crystal, and the crystal is shown on the right hand side. The crystal obviously now consists only of squares at each one of the lattice points, and as I can define a cell for the lattice, I can also define a unit cell for the crystal, which is shown in blue color. Now what is the crystal I have generated? The name of the crystal happens to be a square crystal, and we will try to understand why do we want to call it a square crystal. Now if I look at the symmetry of the motif, you can see the motif is shown here. We see that this motif has got a 4 mm symmetry. So what is the 4 mm symmetry? The motif has got a 4-fold symmetry at the middle, like in the square center of the thing. You can use, of course, this is the symmetry of the lattice. The motif itself has a diagonal mirror and a vertical mirror. So in other words, these are the two mirrors I am talking about, and additionally it has got a 4-fold symmetry in the center, therefore it has got a 4 mm symmetry. Now this 4 mm symmetry of the motif is similar or identical to the symmetry of the lattice. So when I put this motif, and the important point to note here is put it in this orientation which I have shown, then the symmetry of the lattice is not lowered, and the symmetry of the lattice is preserved when I make a crystal. So what is the symmetry of the crystal I have obtained? The symmetry of the crystal is again 4 mm, and the crystal has this unit cell with the symmetry operators overlaid, and you can see that the symmetry of the crystal is identical to the symmetry of the lattice, and therefore I call it a square crystal because of this presence of 4 mm symmetry. Very good question. Soumya has a very good question, that what will happen if I now do not put this motif, which is a square, in a single orientation, and especially the special orientation wherein I can see that the square of unit cell of the lattice and the square is identically oriented. In fact, we will take up this very example in the next slide which is coming up, and we will try to see what will happen to the crystal we generate. So that's an upcoming example. So in this example, we clearly see that the symmetry of the motif is equal to the symmetry of the lattice. In the previous case, the symmetry of the motif was larger than or greater than the symmetry of the lattice. And in that case we had obtained a square crystal. In this case, the symmetry of the motif is equal to the symmetry of the lattice, and of course it is possible that it is equal, and more importantly, more than being equal, the symmetry axes coincide. In other words, I put my orientation such a way that the mirror planes of the motif, which is for instance a vertical mirror and a diagonal mirror, coincide with the vertical mirror and the diagonal mirror of the lattice. In such a process, I see that no symmetry has been lost, and I would get a square crystal, and it would have a symmetry 4 mm. So we will sort of try to generalize the understanding we have gained from these two examples, that if the symmetry of the motif, and of course when I am talking about symmetry of the motif, I am considering also the orientation of the motif with respect to the lattice, is greater than the symmetry of the lattice, then the symmetry of the lattice and the crystal are identical. So this is an important principle we have sort of stumbled upon by considering these examples. So let me repeat it again. The symmetry of the motif, if it is greater than or equal to the symmetry of the lattice, then the symmetry of the lattice is preserved, and you get the symmetry of the crystal being identical to the symmetry of the lattice. Another thing which we will see soon is that this common surviving symmetry determines the crystal system. So we will take up examples next to understand this principle which I have written down at the bottom, that how certain symmetry elements which are common after you have done the decoration, which is what will go on to determine what is the symmetry of the crystal we have generated, and therefore what is the name I would give to such a crystal which I produce by putting these motifs on lattices. So let us consider another example, which is what Soumya had thoughtfully asked me. So this is an example of a same square lattice as before, but only thing I am doing now, I am rotating the motif with respect to the lattice. In other words, it is not in the same orientation as the unit cell of the lattice. Previously we had assumed that the square is favorably oriented, and therefore the symmetry elements are common to both the lattice and the motif. But in this case you can clearly see that the square motif has been rotated, and I for now would assume that the rotation is some arbitrary angle. It is not some kind of a very special kind of an angle. It is not 45 degrees or 90 degrees. It's an any arbitrary angle. I am rotating the motif with respect to the lattice, and I am obtaining a square crystal on the right hand side. Now the question, of course, I have to ask, why do I call it a square crystal? So to understand that, I will have to investigate the symmetry of the crystal I have just constructed. So let us look at the symmetry of the crystal. So I have my square lattice, I have a rotated motif which goes on to decorate each lattice point, and we had mentioned that when we go from lattice point to lattice point, I am not allowed to rotate the entity of the motif, and I have to put it in the same orientation, and that orientation is the one which I have used here. The unit cell is not altered, unit cell remains the same as before. And now if I analyze the symmetry of the crystal which I have generated, you would notice that all the fourfold axes survive. The fourfold which was present at the vertices, the fourfold which was present at the centers, all these fourfold axes of the lattice survive in the crystal which I have generated. And in this process, of course, it requires a little bit of mental exercise to see that actually they survive, and that is left as an exercise to the students. So we see that the symmetry of the crystal is same as the symmetry is lowered with respect to the symmetry of the square lattice, but there is one symmetry element which is the same, which is this fourfold axis at the lattice points and between the lattice points. So when I generate a crystal, now the symmetry of this crystal does not have any mirrors. The vertical mirror which was originally present along this direction, the diagonal mirror. So in other words, if I want to superimpose it here, this is the vertical mirror, and this is my diagonal mirror which was originally present in the lattice. For instance, I show it on the lattice. These two mirrors have been lost. Nevertheless, since you have a fourfold symmetry still surviving, I would call it a square crystal. Now it is the method of classification wherein we include 4mm and 4 both into the square class of crystals. In other words, the characteristic symmetry of all square crystals would be the presence of a fourfold axis, which is why I call this a square crystal, even though the symmetry of this crystal is lower than the symmetry of the lattice I started off with. Mr. Deptos has a question.
So if we differ the orientation of the motifs, then can we consider the motifs as different motifs?
I could not get your question. In other words, when I go from lattice point to lattice point, do I rotate?
The orientation of two motifs, can we consider two different motifs?
In other words, when I put the motif in the first lattice point, I use one orientation, and second lattice point use a different orientation. Okay. Another very important question, let me rephrase Mr. Depto's question, that here in this example, I had used a motif which is just in a single orientation. What if I for instance, use this motif and put it in the first lattice point? I used a second orientation. For instance, I could just draw it here on top, or I will go to the board to draw the second orientation. So this is my lattice. So for instance, I have rotated my first motif in this orientation. I could do an arbitrary rotation for the second shape. I can use second orientation. So I call it O1 and O2 for the two orientations. So this is my motif now, and these arrows show the orientations which I am considering. Therefore, I have my lattice which is in this orientation. I rotate my first motif to a new orientation which is at a certain angle alpha with respect to the original lattice. Further, I can even consider a second kind of an entity which is rotated at angle beta with respect to the original lattice. Now, of course, I will consider first the case of two such orientations, and of course we could expand this to 3, 4 and infinite such orientations. Now suppose in the case of a two orientation, obviously the crystal's symmetry would be lowered further, okay, and it will definitely clearly not belong to the crystal, the square crystal, if I am just using true orientation. In other words, I put on this lattice point with the first orientation. Let me go back to the board maybe. So at this lattice point I put orientation 1, at this lattice point I put orientation 2, at the third lattice point again I will put orientation 1, maybe I will write with a different colored chalk for better visibility, and the next lattice point I will go to orientation 2. But at every lattice point I have only two orientations. In other words, as I move from one lattice point to the other, I just change the orientation. In this case, my motif would not be this O1 or O2, but a combined 2. So, this both might together put 2 will be the motif, and in that case the surviving lattice points would be the alternate lattice points. So, this will be my lattice point, and my lattice translation vector in the x direction will not be this, but will go from all the way from here to here. So, this will be my fundamental lattice translation vector, and this is the case of 2 orientations. The case of 3 orientations would be very similar, and we had already considered that kind of an example when we did an arrow up arrow down kind of an example, but the case of infinite orientations is more interesting, and we will very soon return to that example to understand what will happen in the case of an infinite orientation. It's very important kind of a question, and we will address it very soon.
So here we take a square motif, and that is a 4-fold. If we take some 6-fold, 8-fold, and symmetry will be same, then we get, I think, the actual picture like this.
Okay. Another very important question. Okay. The question, Mr. Patel's question is that instead of now considering a square motif, I could have considered a heptagon, an octagon, or any other n-gon, or any other more complicated shape. So, what we are, very important question, and we will answer it in a set of simple principles, and one of those principles we have already evolved, and the evolution of the principle is that, taking into account the orientation of the motif, of course, if the symmetry of the motif is greater than or equal to the symmetry of the lattice, then the symmetry of the crystal is identical to the symmetry of the lattice. The more lower symmetry cases are the ones we are considering now, and I think your question will be completely answered beyond doubt when we consider the next few examples, which we are coming to very, very soon, which will be the cases of motifs which have more complicated shapes, including the heptagon, the octagon, etc. So, it is purely based on symmetry. So, that is the simple argument we have got. So, the crystal we have constructed so far with this rotated motif, of course in a single orientation, has got this 4-fold symmetry alone surviving. So, the symmetry of the crystal has been lowered from 4 mm to just 4, but still, since it has a characteristic number 4 or the symmetry 4-fold, it is called a square crystal. Okay. Now, let us consider another example which is precisely in line with the kind of question Mr. Patel asked. What happens if I put for instance a triangle, a pentagon, or a hexagon, or any one of the higher order polygons, or more interestingly some very distorted kind of polygons, a non-regular pentagon, okay, a non-regular heptagon, or so forth. But once you evolve the principles, it is very easy for you to deduce what would happen if you take up one of those more complicated cases. Complicated in terms of the kind of motif you are putting, but in terms of language of symmetry, the understanding is very, very simple. So, as before, I start with my favorite square lattice, which has got 4 mm symmetry, and now I put a triangle motif. So, what I have to do, I will have to put a triangle here, a triangle here, a triangle here, and so forth, to infinitely fill this 2-dimensional space. Now, when I do this operation, I do not get a square crystal. This is an important point to note. The lattice is square, the crystal has a square unit cell, the lattice also has a square unit cell, but definitions of crystals is based on symmetry and not merely on the geometry of the unit cell. This is the statement we had made before, and this is a nice example to understand that concept. Now, based on the lattice parameters, if I were to conclude, I would wrongly conclude that this is a square crystal, but clearly this is not a square crystal, this is a rectangle crystal. So, now I have to understand clearly, when I use the word square as an adjective to the lattice, it is a technical term. It implies certain kind of symmetries. When I use a rectangle in front of a crystal, the same thing holds, that I have to worry about symmetries, and in this case I have to worry especially about rotational and mirror symmetries, and we have seen that whenever we have rotational and mirror symmetries, there are also additional redundant symmetry operators which can come about, but for now we do not worry about them. So, it is clear that rotational and mirror symmetries in 2 dimensions would suffice me to understand what are the crystals I am generating. So, I am considering 3 concepts: the concept of the lattice, which is square, the concept of the symmetry of the crystal which I have generated, and parallelly, if I want to define the concept of the symmetry of the crystal, I need to understand the symmetry of the motif. Okay. So why do I call this a rectangle crystal and do not call it a square crystal? In this case, the symmetry of the lattice and the crystal are different, and therefore it is clearly not a square crystal. In this case, we have to note that the word square does not imply the shape in the usual sense. The word square here is a very technical term. When I mean a square crystal, I mean it has got a 4-fold symmetry or a 4 mm symmetry, and I am not using it in the sense of that it has got a square geometry of the unit cell. Yes, additionally, of course, I could take the geometry of the unit cell and analyze its symmetry, which is definitely possible. So let me go down to the board and maybe summarize the various entities whose symmetries we are talking about as we talk. When I am talking about symmetries, and my nomenclature of various kind of lattices and crystals are based on symmetries, I could be talking about the symmetry of a lattice, I could be talking about the symmetry of a unit cell, which could be of the lattice or of the crystal, I could be talking about the symmetry of the crystal itself, which I have constructed from the lattice by putting a motif, and parallelly I need to worry about the symmetry of the motif and especially the surviving symmetry when I put motif on top of a lattice. So I should be clear that there are various kind of entities which I am dealing with in crystallography. I need to worry about the symmetries of each one of them, and often in conjunction with each other. So having summarized this, so let us return to the crystal I have generated. You can clearly see the original lattice had a 4 mm symmetry, but the symmetry of, let me go to the next slide, the symmetry of the motif is mirror planes. Actually, you can draw, let me go back to the board again. So I have a triangle here. This is an equilateral triangle. You can have one mirror plane. So let me draw the mirror plane in a different color. So you can see that there are mirror planes in the triangle. Additionally, you have of course a 3-fold axis in the center, which I can also highlight like this. So this is my 3-fold axis. But this 3-fold axis is not compatible with the lattice. The lattice has no 3-fold axis. Therefore, this 3-fold axis does not survive when I try to put it on the lattice. On the other hand, suppose I call this mirror 1, do I need to consider this as mirror 2? Not, because this mirror 1 on the operation of 3-fold comes down to mirror 2. But when I put this motif on top of the lattice, the only surviving mirror would be this vertical mirror. If I call it V, this mirror and this mirror would be lost. Therefore, I would have a symmetry of the crystal as M. So the symmetry of the lattice was 4 mm. When I made the crystal, the symmetry of the crystal is just a single M, which is the common surviving mirror or the common surviving symmetry element between the motif and the lattice. So there is just one surviving element, which is mirror, and therefore the symmetry of the crystal is also happens to be M, and in this case the symmetry of the crystal compared with the symmetry of the lattice has been lowered, and now therefore the crystal I obtained is a rectangle crystal. Now why do I call it a rectangle crystal? Because M is a characteristic symmetry of rectangle crystals, and this will become clear when I try to classify various crystals in the summary slide. So looking at the symmetry of the structure has only one surviving mirrors. The unit cell, as before, conventionally can be chosen as the blue square whose lattice parameters have not changed, and my crystal is now a rectangle crystal. Now what is wrong in calling this crystal a square crystal? Okay, let me try to use a sort of a common sense kind of an example to understand why this cannot be called a square crystal. Okay, so let me go back to the board. So now the crystal I have generated is made up of now. Instead of making this crystal, and let me compare the crystal which I had made before, which is the case of the square crystal, or let me even consider for instance the case of the crystal made by putting circles. So it does not matter for my argument if this is a circle or a square, but I want to point out that it is not merely without reason that I would consider this as a rectangle crystal and call this a square crystal. So there is no, it is not without reason, it is not without common sense, and there is a simple sense of logic which is built into it. Let us assume now I am sending, these were some obstacles which I put, some blocks of wood which I put on a plane surface, and I am passing water from the top direction. Now obviously for this crystal, when I pass water from the top direction, so there will be a certain flow of water, and these are now wooden pegs for instance which are blocking my flow of water. It would not matter to me for instance if I send my water in this direction, right, or I send my water in this direction, or I send my water in this direction. For this crystal, it has got a fourfold symmetry with respect to its properties also. So its properties, for instance, now its resistance to the flow of water, the way it interacts with water is absolutely the same irrespective of send my jet of water in this direction or flow of water in this direction or any one other direction. Clearly for this crystal it would make a lot of difference if I may send the water in this direction or the other direction which is the opposite direction. So these two directions are not equivalent for this crystal, right. However, because there is a mirror plane which I showed you before, please forgive me if I can't draw the mirror plane correctly, this is a mirror plane. What it means that there is no horizontal mirror. What it is telling you, this is not equal to this, is there is no horizontal mirror. The properties of flow of water from the top direction would be very different from the properties of the flow of water from the bottom direction. But now since this has got a mirror plane, if I send water in this direction or water in this direction, they will be equal because it's got a mirror plane. So this flow can be inverted to this flow by the mirror, and therefore flow in this direction would be identical to the flow in this direction. But please remember, this structure has a fourfold symmetry. So I can for instance draw that fourfold axis here, or of course it is also located at the lattice points, right. That means that this arrow mark can be turned to this arrow mark by the presence of the fourfold axis. Like for instance this was turned to this arrow mark by the presence of this mirror, but this arrow mark cannot be turned to this vertical arrow mark by a, because there is no fourfold, it cannot be turned to this direction. So clearly for this structure, this direction, so this is not, no transformation like this is possible. Clearly for this structure, the flow from this direction is identical to the flow from this direction, but the flow from the top or bottom directions are not identical, and they are not identical to the flow from this direction either. So when I am considering properties, obviously the symmetry of the crystal matters to me. Of course I have to choose a property which is sensitive to the crystal structure, right. For instance, suppose instead of passing suppose these were wood pegs and I pass very high energy neutrinos, then it may so happen that the neutrinos will not interact with my wooden beams or wooden or paper obstacles which I am putting here, and therefore I would not see the difference between these directions. So it is clear, as long as I am looking for a property which would be determined by the symmetry of the crystal, like for instance in this case we consider flow of water, then I would clearly make out the difference between two directions, and only those directions will be equivalent which would have the same symmetry. So it is not without reason that I call this a rectangle crystal and not a square crystal. So let us consider some of the example. So there is something more, perhaps we will just complete this topic of the triangle crystal. So we see in this case that the symmetry of the motif is lower than the symmetry of the lattice, and of course as far as the threefold axis goes, it is even incompatible with the symmetry of the lattice which had a fourfold axis. The lattice had 4 mm symmetry, the motif had 3M symmetry, it had a mirror and a 3-fold, it had a 3M symmetry, and the surviving symmetry for the crystal was just an M. The symmetry of the motif determines the symmetry of the crystal. It is lowered to match the symmetry of the motif, common symmetry elements between the lattice and the motif which will survive, i.e. the crystal, that is, the crystal structure has only the symmetry of the motif left, even though the lattice started off with a higher symmetry. So this is an important example, and you should bear in mind this important example and try to correlate it with the properties of the crystal whenever you are dealing with the property aspects. And now again, to re-emphasize, the word rectangle in the context of the crystal denotes the symmetry of the crystal and not the shape of the unit cell. So we come across the second principle, that if the symmetry of the motif is lower than the symmetry of the lattice, when I am talking about the symmetry of the motif, I am also worried about the orientation of the motif. Like in this case, suppose I had rotated the triangle, then there could be no symmetry element common between the lattice and the motif which could happen. I arbitrarily rotate the triangle, therefore then in that case the symmetry of the crystal will be even lower. So the symmetry of the motif, if it is lower than the symmetry of the lattice, then the symmetry of the lattice and the crystal are not identical. So this has to be absolutely clearly borne in mind. The symmetry of the lattice is lowered with only common symmetry elements surviving. So this is an important rule, and we will of course consider more physical aspects when we come to the concept of more realistic crystals which are made up of atoms, wherein what happens if I put motifs of lower symmetry, that will also has to be considered in a different way. So this is the case where I was talking about, wherein the triangle motif has been rotated with respect to the square lattice, and in this case I told you there is no common surviving symmetry element between the lattice and the motif, because the original mirror, even though the motif continues to have its original symmetry which is 3M symmetry, the lattice continues to have its original symmetry which is 4mm symmetry, but the crystal itself which I have generated has no symmetry except translation. This is an important point to note. Even though it has lost all its possible symmetry, it still has translation, and such a crystal I would call a parallelogram crystal. And why I am using the word parallelogram is now related to the symmetry and not to the geometry which I usually associate with the unit cell. The unit cell, as before, continues to be a square unit cell as before for the lattice and for some of the crystals we have generated before. Again, the choice of the unit cell is left to us. Even for the same crystal, I could go and make a choice of the unit cell. For instance, I can start from this lattice point, go here, go to this lattice point, and I make a unit cell like this. So this choice I could make, though the preferred unit cell will still be the blue colored unit cell, and you can see that the red outlined unit cell is a doubly non-primitive unit cell, and this choice I can make. Why I would make would perhaps be determined by other factors, but this is, the red unit cell is as valid a unit cell as the blue unit cell, though the conventional unit cell for such a structure would be the blue unit cell. Let us consider some more examples in 2 dimensions, and some of these examples are pretty intriguing, though often it is still in a very mathematical sense, but we should not forget sometimes nature gets very close to mathematics, and we have to use some of these tools to understand some of the real structures which exist in nature or have been produced artificially in the lab. So let us start with our old friend, the square lattice, and now I put a motif which is pretty random shape. Of course, this random shaped object could be replaced with any other random shaped object you can think of, and this will work extremely as fine as the others. So this is my motif, which is, I have tried to start with a circle and make it as random shaped as possible, and I have tried to make this motif as a entity which will go on to generate this square lattice of mine. So now if I put this random shaped motif, of course again I make sure that I follow the rule of a single orientation on each one of these lattice points. I would obtain a crystal which is shown on the right hand bottom corner. Now if I look at this crystal which I have generated, it is clear that no kind of symmetry element would survive in this crystal except translation. So the symmetry of the lattice has been lowered to the maximum possible extent. There is no rotational symmetries, no mirror symmetries surviving in the crystal, and the crystal now as we had considered one of the examples before, is a parallelogram crystal, and it is definitely not a square crystal. If I want to call it a square crystal, we had seen that we have to have a 4-fold or a 4 mm symmetry, and this crystal which I have generated here with this random shape motif has only translational symmetry, and that is absolutely a must for something to be called a crystal, because that is how I generated the lattice. So, there are two translations surviving, the A translation and the B translation, which is common to both the square lattice and to the crystal I have generated using the lattice. So, this is clearly a case of maximum possible lowering of symmetry, except for the case which I am considering now. In this case, what I am doing, I take the same square lattice, I take my same random shaped object, but what I do, as I go from lattice point to another lattice point, I rotate this object at various random orientations and put them. For instance, at this lattice point, this edge is oriented in this direction, in the next lattice point it is oriented this way, third a little different, fourth a different, some other lattice point it is oriented this way, in this way, and so forth. So, at each lattice point, the entity which I have now considered, and I have to be little careful in now using the word motif, because when I am using the word motif, I will have to make the assumption that it has been placed identically at each lattice point. Now, I will use a more general term like an entity. So, this entity has been put at each one of these lattice points in a very random way, and in this case even the translation which I had in my lattice, which is sort of the very basic a lattice needs, or the two translation vectors in 2 dimensions, has been lost, and what I am generating here is not even a crystal. And since it is not a crystal, I can't even have an unit cell for this. So, however, you might see that is it now logical for me to completely throw away all my language of crystallography? This is a question I can ask to understand this structure I have generated on the right hand side, which I call an amorphous material. I do not call it a crystal anymore, and as the reason being that to something to be called a crystal, the minimum surviving symmetry has to be translation, and since this does not have translation, and the reason it does not even have translational symmetry is because I have sort of rotated this entity as I go from point to point, and this is precisely the question which Deptos had asked before. What would happen if I start putting this entity of mine in multiple orientations? As long as the multiplicity remains finite and in a very well ordered fashion, it is fine, but if I start putting it as randomly as the case I am here, then you do not have a crystal. Now, the question we have to ask further, and we will of course answer this question a little later, is that do I have to throw away all my crystallography concepts which I have generated so far in understanding the structure I have generated? The answer is no. We can still use some other concepts of crystallography, and now when we, of course this will be considered later, is the fact that when I am not so strict with both my positional and orientational order. For instance, now I see that if the center of mass of this object coincides with the lattice point at each lattice point, I still have something intuitively, it tells me that there is something left in the structure which I can use my language of crystallography to describe, and we will take up that particular concept in a later lecture. So, let us summarize the 2D crystals we have generated so far. We have 4 kinds of crystals in 2 dimensions, and they come in 4 symmetry classes. The square crystal, which has 2 kinds of allowed orientational 2 kinds of point group symmetries, which includes the 4 mm and 4-fold, the rectangle crystal, which includes the 2 mm and m, the rhombus crystal, which includes the 6 mm, the 6, the 3 m and 3, the parallelogram crystal, wherein just you have 2-fold, and finally you can conceive of a situation wherein the case before, where there is no symmetry left. Now, we of course can use lattice parameters and to describe these kind of crystals, and then when I am talking lattice parameters, I am talking about a preferred unit cell or the conventional unit cell, and we had seen that for a case of a square crystal, this would be the preferred one, A equal to B alpha is equal to 90 degrees. In the case of rectangle, A is not equal to B alpha is not, alpha still happens to be 90 degrees, and so forth as listed in this table. Now, I have put these symmetries as a highest possible symmetry and other possible symmetries, and it is for a reason, because the highest possible symmetry is the symmetry of the lattice, I can always choose motifs, for instance the circle motif being the highest one, such that the highest possible symmetry survives. In fact, there is a technical term which talks about the highest possible symmetry, and the word used is holohedral. The other possible symmetries are lower, but still if these symmetries survive, I can for instance put a crystal under the rectangle class even if a single mirror survives, or in other words it is still has got a single mirror. A curious point to be noted is that the 3-fold and the 6-fold both come under the rhombus crystal. This is, as when we were discussing lattices, we talked about this specifically, this very point, that sometimes you have seen representations of unit cells of this 120-degree rhombus wherein there are 6 folds, and some cases where there are only 3 folds. Because of the convention, all these kind of symmetries are put under the rhombus class, and we will see later that when you go to 3-dimensional crystals, the crystals with 6-fold symmetry are placed separately from the crystals with 3-fold symmetry, which has not been done in 2 dimensions. They all come under the 120-degree rhombus class, and we have to still note that lattices will always, hexagonal lattices will always have 6 mm symmetry, while crystals based on them could have a lower symmetry. Now let us try to make some crystals in 3 dimensions. As before, I start with a 3-dimensional lattice. I put a 3-dimensional motif, and the lattice I have about 14 choices to choose from. I have the 14 Bravais lattices from which I can make the crystal, and let us for instance in this lecture series consider a few simple examples, especially the ones important from the point of view of material science, which we will make crystals with. So this is the simplest example I can think of. This is the simple cubic lattice, and I can put a sphere, and in this case I have been previously using circles with also the shading effect. Please remember, here I have given the shading effect specially to show that it is a 3-dimensional object, a sphere, and I put the sphere at each lattice point. The crystal I would get would be a simple cubic crystal, and which is shown here. Now a few things have to be noted when we show diagrams like these, is the fact that if these were hard spheres, then in other words these were spherical atoms, then the atoms would be touching each other. The kind of model which has been shown here is called a ball and stick model. Now in reality, you know that atoms need not be spheres, they can deviate from their spherical shape quite a bit, but in introductory lectures we will assume that some of these atoms are spherical. That means they have a shape like this, and we know that suppose the s orbital has a spherical symmetry, but some of the other orbitals do not have spherical symmetry, and in reality atoms can sometimes be considered spherical. They are very close an approximation to a sphere, but at other times they are not so, and therefore our hard sphere model would break down. But for now, since we are doing some mathematical crystals and of course slowly entering into realistic crystals, we will assume that these atoms are spherical. Now I was talking about the models, and let us see what kind of models typically we use to represent crystal structures, because often in 3 dimensions it is very difficult to visualize crystal structures, and therefore we need to use multiple kinds of models to understand these kind of crystal structures. For instance, there are 4 kinds of models which are commonly used. The one on the left hand top side is called the wireframe model. In the wireframe model, you have the lattice points or the atoms shrunk to points. In other words, I do not show my atoms explicitly. What is in emphasis are the cell edges. So the cell edges are the ones which are emphasized, and the atoms or the entities which are decorating the lattice are shrunk to points, and my unit cell is in full view. So this is called a wireframe model. In a ball and stick model, you have these kind of spheres which are balls, and there are these unit cell edges, both are in view, and this is called a ball and stick kind of a model. And clearly you can see from this that the atoms are not touching each other. You can have something known as a space filling model. In space filling model, atoms would touch each other, but unit cell edges may not be visible. So this is an important note. In this case, the unit cell edges take the lower priority, the lattice points take the lower priority. It is the atoms in full view touching each other. Okay, that is what is called a space filling model. We have to note that an important point to note regarding space filling model is that, and perhaps we talked about this a little bit when we consider the concept of a space filling, that even though we call it space filling, it is very clear that it does not fill up entire space. Spheres, for instance, cannot fill up entire space. There is void, as you can see from this picture, left inside these or between these atoms or spherical entities, and so we have to understand that even though called as space filling, it is truly not space filling. Finally, there is an extreme kind of model, which is what is called a void model, in which case the void is in full view, and in the case of a cubic crystal, suppose I try to put an atom at the center of this unit cell, which is right at the center, and the position of that center would be half, half, half. I try to put an atom, of course, which would snugly fit into this void. Then that atom, which is of course an atom not belonging to this simple cubic structure, would actually be touching all the 8 atoms. So as far as that atom goes, the void around it is in the shape of a cube. So in this case, the void is in full view, the atoms and other entities have been hidden away. For instance, you don't even show the lattice points here in this model, while in a wireframe model typically you would like to superimpose the lattice points. Now, as we shall see later, in this particular structure there is only one kind of a void, but there could be structures, as we shall see later, where there is more than one kind of a void, and therefore we have to show all the possible voids. The void happens to be a polyhedron formed by the vertices of the void. Okay, that is what we are talking about, a void here. We are not actually talking about the real shape of the void, and maybe a little later I will show you how the real shape of the void could look, which is the space between the atoms. Okay. And here in this void model, everything else has been hidden away except the void shape, or the polyhedron, which we consider as the void shape. So I have in front of me an example of the 4 kinds of models I was just talking about. In addition, I have got a 5th kind of model, which I will talk about. So on the left hand side, I have got an yellow wireframe model. This is my ball and stick model. This is my space filling model, and here I have got my void model. As you can see in the wireframe model, which I will pick up and show you in perspective, the vertices are the seats of the lattice points and of the spherical atoms. And these wireframe models are important for us to understand the connectivity and also perhaps the unit cell shape. So here, this is the first class of models which I can use, and we will see more examples of these kind of wireframe models when we go in the course along. The second model on the right hand side is the ball and stick model, and in the ball and stick model we have the unit cell, we have the balls, and the unit cell edges have been colored in red. Clearly, you can also visualize certain connectivity if you have a ball and stick model. I will take another example just to tell you how we can overlay connectivity along with the concept of the normal ball and stick model. To do this, let me take up another example. This is a slightly complicated example which will come up very soon, but here you can see in this ball and stick model, you can see that this atom is touching this atom is touching this atom. So the cell edges is not the direction along which the touching is done. So therefore I can introduce the connectivity between atoms, or the what you might call the proximity can also be shown along with the concept of the unit cell and the structure. So there are more complicated ways of showing my structure using the ball and stick model. The third model here is a space filling model. You can see here. So you can see that these balls are touching each other. So if I look along the top direction, this is now my 3-fold direction of the cube. I can clearly see that this ball is touching this ball is touching this ball is touching this ball, and so forth. You can see how the atoms which are represented by these white balls are touching each other. Now let me pick up this model and show you in a little bit of rotation. So this is my space filling model, and as I pointed out, clearly even though it is called space filling, I can clearly see the voids. As you can see, perhaps there is a void at the center, and I can use a straw actually to go through these voids. So I can see that there are voids, which, for instance, this void is along the 1 0 0 direction, for instance this is the other direction, and the third perpendicular direction. You can see the voids in this, and clearly if I were talking about crystal structures, I could, as I was pointing out, you can put an additional atom which can go and sit inside this void. Okay. And now if I were talking about an additional atom sitting there, then it is inside the void of this unit cell, and that is when we find handy to talk about the void models. So that atom sitting in the center of this unit cell will be touching the 4 atoms in the top, the 4 atoms at the bottom, and therefore 8 atoms. So the polyhedron formed by the vertices of that coordination is polyhedra is nothing but this void, which is a cubic void. Now you can clearly see this is space filling. That means I can put these kind of unit cells together in 3 directions to get a space filling. Now I cannot do, technically speaking, I cannot do space filling with these 2, and therefore I need to consider another kind of a model, which is this model, which you can see here, which is truly a space filling model. In other words, if I were to put one unit cell of this, an identical unit cell of this to the right hand side, this white units with these white balls, then you can see that this half of the atoms will overlap. That is not allowed. Therefore this is technically not the unit cell of, or for instance matter, this, both of these cannot qualify as the unit cells of the simple cubic crystal. For the simple cubic crystal, this is my unit cell, wherein there are 1/8 of atoms which are present at each lattice point. Okay. So I have cut my single sphere into 8 parts and I have put them on the 8 corners of this cube. So this is my model, wherein I have got my cube, wherein you can clearly see that now the atoms are 1/8 of the original sphere. So this is truly speaking my unit cell, and when I put another unit cell next to it, another unit cell next to it, and I do so in all 3 dimensions, I would get a crystal. So I have, in summary, I have about 5 type of models which I require when I want to understand crystals: the wireframe models, the ball and stick models, the so called space filling models, the void models, and one more kind of a model which is what you might call a space filling, but with a true representation of the unit cells. Mr. Patel has a very good question now. Can we use octahedral voids? Is that your question?
Yeah, I want to fill this void with any octahedral field. Can it be possible?
Okay. So this is a void now, for instance, right? Now I could have voids in various shapes. What kind of shape of void would depend on the crystal I am constructing, right? And if I am going to have a single shaped void, as in the case of the cubic, simple cubic crystal, or there are going to be more than one shape of void, is the first question I would ask myself. As we shall see in the soon upcoming example, that for instance in the face centered cubic crystal, there are 2 types of voids, the octahedral void and the tetrahedral void. Okay. Now the important question is that we know for sure the cube is a space filling solid. Cube can monohedrally fill space or monohedrally tile space. So this concept you have already seen, right? So all I need is a shape of a cube. I can arrange it in 3 dimensions to fill space. And in fact, if I don't impose the constraint of a vertex to vertex connection, we had seen that there are infinite many ways of filling space with just the cubic shape. Now we had already pointed out that octahedra is not a space filling solid. In fact, we will see very soon that octahedra in combination with tetrahedra can only fill space, and of course there could be other combination, but in the special case of the face centered cubic crystal, we will see that these 2 shapes of voids go on to fill space. So if I want to use octahedra, it is not the regular octahedra in this case, it is not possible for me to fill space at all. So if at all, if there is an octahedral void in my crystal, then there has to be an additional void of certain other shape, and in the case of the face centered cubic crystal, it is a tetrahedral void, so that I can go ahead and fill space. So this is a concept which is purely coming from space filling constraints, and therefore octahedral voids alone cannot fill space. So I cannot have a structure which has just octahedral voids.